Bueno, buenos días a todos y a todas. Bienvenidos y bienvenidas a esta segunda parte de la sesión temática de Water Waves. La primer charla del día de hoy será la continuación del minicurso del profesor Alexander Roma. Profesor Alexandre, si gusta.
Good morning.
Good morning.
Morning.
Okay.
I'm sorry, I was using the same link as yesterday. I don't think we are the same, right? I'm sorry.
I did the same thing.
Yeah.
The important thing is that you're here now.
Yeah, okay.
Okay. So we are going to continue with Professor Alexander Roma mini course. So welcome, Professor. The floor is yours.
Thank you. I will share my screen then. Sound optimized, the desktop. Can you see me here and my
Yes, we can.
Perhaps? Okay, thanks. Let's do this. Okay, so good morning, everyone. Here is almost lunchtime already, but it's still morning. Let's continue our talk, our series of talks. Okay, yesterday we have had 2 of them and 2 hours basically, and today I will try to finish the contents that I planned to speak about. As I explained yesterday to Professor Andrade, I considered preparing material for advanced undergraduate students. So I will still pursue that goal, thinking that perhaps someone can, see in this area something that he or she would like to pursue as further studies and everything. So it's more like a motivational mini course than anything else. I hope we can serve that purpose later, since it's being recorded. Okay. So yesterday we reached to this point here. I briefly mentioned every step that we need to mathematical model some Newtonian fluid in an incompressible flow. Okay, so just reviewing a little bit, we had to state several postulates which were in the direction of assuming certain properties of the material flowing. We call them constitutive or constitutive hypotheses, how the medium behaves, how it flows, and how the material it is composed by behaves. Okay, so we assumed as a undeniable truth that Newton's second law applies to the medium, to the fluid. No matter small the region that I consider, it holds true the Newton's second law. Besides that, we are under Cauchy's stress postulates. Cauchy stated that the stress forces, the contact forces acting on the surface of a fluid element, a fluid region, depends only on time, on the location, and on the orientation of the normal vector, okay? And based on that, on these 2 postulates or on these 2 sets of undeniable truth assertions, we arrived at something called local equilibrium for the stress forces. Based on that, we can prove some properties for the stress forces. And at the end, using some classical argument called Cauchy tetrahedron argument, we can prove that under all those assumptions, we have the stress forces given by a linear transformation of the normal vector, which is a very surprising result. Other than that, we assumed that by Boltzmann postulate that this matrix representing this linear transformation is symmetrical. Okay, so after that we arrive to the Cauchy form of the balance of linear momentum, and on the top of this ice cream, our cherry was a series of statements made by Stokes when he was only 26 years old, right? And with Stokes postulates and assuming that the matrix depends linearly on the formation of the fluid element, we finally could write the equation for the balance of momentum of a Newtonian fluid. So it's a pretty long story, and it takes actually several hours to make it in all details and reviewing material from linear algebra and things like that to get to this point. Okay, so I don't know if I did well enough, but I think within the time that I have, it was the best that I could do, I think. So at this point, we have this mathematical model. Incompressible flow of a Newtonian fluid, okay? Rho is the mass density, also called specific mass. U is the velocity of the flow. Here we have acceleration given by the material derivative. Here we have incompressibility of the medium, of the flow, right? F is external forces acting on my material volume. And since we have the Newtonian fluid, this is just contact forces. Gradient of pressure, dynamic viscosity of some diffusion. This is basically friction, okay? So this is where we are standing. I wish focus now on some specific modeling. I like very much fluid structure interaction is my original background. So I would like to use the opportunity to say a few things about modeling fluid structures, interactions, but in a special case when you have elastic boundaries immersed in the fluid. So if you have elastic boundaries, you can think of modeling, for example, muscles, heart muscles. You can model, for example, heart leaflets, and you push the model to mathematical model some quasi rigid structures as well. I will show you some examples of that. So let's start with the simplest things possible, okay? So let's start thinking of a segment, an elastic fiber immersed in fluid, okay? So the elastic fiber is this S, more or less S-shaped curve here. It's just one-dimensional. I will think of two-dimensional applications. It's much simpler to explain, easier to represent in pictures and everything. So let's reduce our dimensionality and think of two-dimensional applications or two-dimensional modeling, okay? So suppose you have a region called omega. This is just a piece of the domain where some fluid is flowing. And immersed in that region, I have some elastic fiber. I am representing here just a little bit of this fiber here. And in particular, I will study what happens in terms of applied forces in just a little bit, a small segment between x at S1 and x at S2. You see, now I am using Lagrangian coordinates. With this capital X here, I am marking on a specific point on the fiber. So S is called the Lagrangian parameter. You assume that you can parameterize the curve with this parameter S. So S is within some interval, the Lagrangian set of parameters, and for each S you have one specific point on the elastic fiber, on this curve. Okay, T is the time again. So as time passes, the flow acts, transporting this fiber segment with it, right? And for each time, for each instant of time, x S1 will have different positions inside the omega domain, okay? So this is how we do that. Consider now just this little segment. So the idea here is that you perform some kind of balance of momentum or equilibrium of forces acting on that segment. For those of you who had an engineering background, it's very common in the very first mechanics courses. You take a structure and you analyze piece by piece of that structure. You remove some certain piece, and you take into account all forces that are acting on that smaller piece of the structure. I am doing here the same kind of thing, right? So let's study closely a elastic fiber segment between this point here and this point there. What are the forces that are acting on that segment? So you have basically here, in the absence of any other kind of forces, right? I am supposing that the only forces that are playing some role here are the elastic forces and fluid forces, okay? So if you get this piece of segment, you have here tension forces. So you have two pieces of immersed boundary, and between these points, you have one pulling the other one, right? So you have tension forces between consecutive or contiguous elements of the immersed boundary. So this tension force here acts along the tangent direction, and it's caused by this other part of the immersed boundary, okay? Here I have the same thing. I have a tension force acting on this point, at this point, and it's caused by the the remaining part of the immersed boundary connected to it over there. Okay, so besides these two forces, these tension forces at the tips, at the ending points of this segment, we also have here some force which is the reaction, it's forces from the fluid are acting there, right? So at every point here in the middle, okay? So we have basically these two kinds of forces. So let's write down the balance of forces. It's like Newton's second law for that little piece of immersed elastic fiber. Okay, so the amount of linear momentum suffered or perceived by that immersed boundary segment is just the total, it's the integral of the momentum, linear momentum for every single point inside belonging to that segment that I'm looking closely, right? So the rate of change in time of the total amount of linear momentum of that little segment of immersed fiber equals to, you know, resultant from external forces and forces at the ending points, right? So the forces at the ending points are the tension forces, which is just a force strength in the direction of normal tangent vector, okay? And also all that forces that act in every point between the tips, the ending points. I'm sorry, but the picture and the mathematics here are from different times in my life. This little f here actually should be a capital F. I'm sorry for that. I forgot to correct the slide. So this is the F acting over there, and this is the resulting force, the total force, right? So here we have we can apply here the fundamental, but let me explain piece by piece. This is the mass density of the elastic fiber. T is the size of the tension forces, is a scalar. This is a vector, the unit tangent vector, and this is the force acting on the immersed elastic fiber. Is a reaction from the force applied to it by the that it applies to the fluid. Okay, so usually you think of this tension magnitude as depending on tension modulus, depending on the strain, how much I can stretch the elastic fiber, which is this thing here, right? Depends on the point at the elastic fiber or on the elastic fiber, and depends on the time. And the tangent vector is just this thing here normalized, okay? So one mathematical hypothesis is that the mass that I have for this elastic fiber is so small compared to the mass around that I can neglect it. So if the immersed fiber has a negligible mass, that I mean by that this is 0, right? This side here is just 0 because it's so small compared to the other stuff, right? That I have these two terms equals to 0. if the sum of these two terms is equal to 0, you can just, put them one equal to each other, right? So if I do that, I can apply now the fundamental theorem of calculus here. So this is like the difference of a function computed at the ending points of an interval or something. And I can rewrite as the differential of this regarding to S. So this is the primitive form, right? This is the integral. So if I want to apply the fundamental theorem of calculus, this is just the integral of the derivative of the differential regarding to S of this function here. So this is basically what's written here, right? So I can just put the two things inside the same integral sign. And since the segment that I'm considering is just any one, it's arbitrary, I can just, and I'm assuming continuity of the integrand, I can just write that this is 0, therefore I have the function arising at the immersed fiber given by this mathematical expression. So all these thoughts take me to a mathematical model of the elastic force acting on the fiber, right? So this is how it is. So this, in this special case, is the Lagrangian force. Is a force that is applied to each point, to each Lagrangian point representing the immersed fiber. Okay, so this is just part of the story that I want to tell. Now, this is the force on the fiber, but now the fluid itself has to perceive, has to suffer the action of this force. So how do we do the connection now that I know how to model the elastic force on the fiber? I know that this kind of force is being generated by the fiber. How I take into account in the fluid equations, right? This is a question. I have to connect both. Yesterday, someone asked me how I can change the model and everything, and I said that we usually do these things by several layers. We keep adding more mathematical formulas and which models other characteristics of the flow or of the problem, and this is how I'm doing this now. It's just an example of what I said. I have, I removed from the elastic fiber a piece of it, and by some considerations and some mathematical hypotheses, I arrived to the conclusion that this is the elastic force fiber for the fiber points, and now I have to connect that with the fluid. So how do I do that? Let me try to show you. You have to consider that this little bit, this small piece of fiber is contained in a region that we can call it R. So I have a region and that contains a little bit of the fiber. So pick any region, any arbitrary region that you like that contains a little bit of the fiber. So, and let now make some observation and take into account all the forces that act on the fluid inside that region R. So I want to learn what happens with the fluid inside that region. I will compute the resultant force just inside that region. So F is the Eulerian force, the force that acts on the fluid, okay, inside the region R. So the resultant force acting on the fluid or in the fluid at that region R is this thing given here. So if we don't have anything else acting on the flow or coming from inside the fluid, the only source of forces that I have is the elastic fiber contained in that region R, okay? So this is what's written here. So the resultant is just the summation of all elastic force coming from the fiber inside the region. So I have to choose, I have to consider only the points inside the region. At those points, I have forces, and those forces are the only ones that matter, considering the region R, okay? So this is how we do it. So the resultant of forces perceived by the fluid come only from all the elastic forces in the segments contained inside the region R, okay? So this is how we write it, right? But I can rewrite this integration in a different form. I could just write an integral on the entire elastic fiber, but I can use some mathematical trick, and this is the characteristic function of the region R. A characteristic function of some region is a function that gives returns 1 if point is inside the region, and it returns 0 if the point is outside. So these two integrals are the same. I am using here a characteristic function of R, and I am calling it, its argument is are the points of the fiber. So if the point, if a certain point of the fiber is inside the region, it returns 1. If this point is outside of region R, so it returns 0. So these two integrals are really the same. And then using a little bit of Dirac-Delta's function definition, we can rewrite the characteristic function as an integral over R of the delta function centered at points of the elastic fiber. So the characteristic function of region R computed at immersed elastic fiber points can be rewritten as this integral over the delta function. From now on, we perform some manipulations, algebraic manipulations, switch the order of the integral, right? And what I have here is that for any region in the any region where the flow is happening, an arbitrary region, I have this integral equal to this other one. Since the region is arbitrary, it happens that the integrand here must be equal to the other integrand there. So F is just the Eulerian force that I have to include as an external source of forces in the momentum equation for the fluid flow is actually this expression here, and it comes from the elastic forces on the fiber exactly on the points of the elastic fiber. So this is how we derive which forces coming from the elastic fiber points are acting on the fluid. So this is an Eulerian representation, and this is a Lagrangian representation. Okay, so in summary, we have here a mixed Euler-Lagrangian formulation for an application involving incompressible flow of a Newtonian fluid with some elastic fiber interacting with the fluid, right? So it's a long mathematical model, but it's the simplest one that I could come up with. So I could show you more or less the steps that you have to take to, to develop a mathematical model for this situation. So these two here are written in Eulerian variables, and they are regarding the fluid flow, the incompressible fluid flow. This F is the force that the elastic fiber exerts on the fluid. The elastic fiber is seen as if it were pure force generator. Since it doesn't have any mass, remember that this is a mathematical hypothesis that we assumed before, right? So since it doesn't have any mass, it's an imagination, it's a mathematical model, right? And it's can be seen as a pure force generator, right? And it would be here playing the role of an external force, right? Pressure, viscosity, right? And this F here that comes, that go in the equation number 2, Navier-Stokes equation, is just computed from the elastic forces that the elastic fiber gives origin, right? And this F here is the tension force. In the case of a simple elastic fiber, this Eulerian force is just the rate of change along the fiber of tension times the unit tangent vector. So this is how the force is computed in this case. If you didn't do that, you could just forget this and depart from this formulation for more general models. This F is always like so, but then you can adapt, you can derive different kinds of F depending on the kinds of structure which is immersed in the fluid. Okay, you can try to model using this formulation, rigid bodies and interface forces acting on interface between two different fluids. I've done that in the past. It works pretty well, right? I will show you some examples how you can, you can just switch capital F by other things and model different kinds of immersed structures in the flow. It's a very powerful mathematical model, very versatile. You can use for several kinds of applications, okay? But it needs one equation, which is the equation that gives us how this immersed structure flows with the fluid, okay? So here I have the Lagrangian velocity for the immersed structure points, right? And we are supposing that there is no slip condition valid. So the fluid doesn't slip on the surface of my immersed structure. Both points that are in contact with the fluid have the same velocity as the fluid, right? So this is the fluid velocity, and I use here the delta formulation to perform something that you can call interpolation. So I have the fluid around the structure points, and I have to interpolate this fluid velocity to the immersed structure points. So this is the complete model. How the structure moves, how it applies forces to the fluid, and this is the complete model. Okay, so this is called immersed boundary model. And as I told you, if you don't consider elastic forces, you can just model these structure forces any way that you want. Okay, so but originally the forces came from muscles, so they resemble this modeling here. Okay, how do I solve these equations? Well, there are several ways of doing it. You can try to use finite volume methods. You can use finite differences methods. You can use finite element methods. Nowadays, you can find literature using several kinds of discretizations and different even programs that you can download and try to use and everything. There's a lot of material. This methodology is basically 50 years old. It was first proposed in the 70s. Okay, so it's old, relatively speaking, and there is a lot of things done. There is a huge community, scientific community using it and developing it and sharing results and sometimes even codes, right? Computer codes. So, well, I am show you a little bit. I will make some comments on how to do it using the finite differences approach. Right? So you have here the complete set, right? So you have Eulerian variables, you have Lagrangian variables here and here, and you have an immersed fiber, Lagrangian representation, and that's how we will do it. For the region of the flow, we just use a fixed mesh, a computer discretization or a numerical discretization for the region where the fluid is flowing. So I set up a mesh, and the unknowns you can locate wherever you want. In this particular example here that I'm, just to show you a little bit how this is done, I am using the crossings of horizontal and vertical lines. So you have here, for example, at these nodes, you have the velocities, the fluid velocities defined, you have pressure defined, you have material properties defined, everything you may want to discretize regarding the flow. And the fluid, you just assume that they are defined at nodes of this grid, okay? And you will approximate the solution of that model, mathematical model, only on these grid nodes, okay? On the other hand, you have here a piece of immersed boundary, and you also have to perform some kind of discretization, and the black bullets are the points on the immersed boundary or along the immersed boundary that I will consider. So I have these points where I will approximate the solution of my mathematical model. Okay, so Eulerian fluid flow variables are located at grid nodes, Eulerian grid nodes, and for the immersed fiber or for the immersed structure, you just use a different set of points. They do not coincide with Eulerian grid nodes. They are anywhere inside the region, and they move. Okay. Finite differences, for those of you that didn't have yet the opportunity of meeting them, it's just based on values of the function in points that are relatively close, and they somehow must approximate the derivatives. So it's a finite difference. It's a finite difference because I am not taking to the limit when the distance between the points go to zero. I just fixed finite distance and compute this finite relation here. And I do that for in the directions that I need, the x direction, y direction, in time, and everything, right? So I approximate derivatives, differentiation, by finite differences. And then I have an algebraic set of equations to solve in the computer. So the discretization processes using finite differences, I just transform the continuum model, the differential equations, the partial differential equations, into a set of algebraic, often nonlinear set of equations that I have to solve in the computer. Okay? So here I have the gradient operator, here I have the divergence operator, here I have the Laplacian, a discrete operator, and I have a huge set of algebraic equations that I have to solve. Just to, you know, so you can look at it, how ugly or how long this is. This is the set of discrete, this is the discrete set of equations. My mathematical model here is translated into a set of algebraic equations that you have to solve simultaneously inside for every point in the domain, the grid or Eulerian grid domain, and for every point of the immersed elastic fiber. So originally I called this a simple model because this can become much more complex, right? So, but in this version of the slides and the notes that I handled out for the organizers, I think I just erased the word simple because this is misleading actually, right? It's simple related to the other ones, but if you see that for the first time, I think it's pretty complex, right? So this is how you do it, and you make the computer solve these equations to get approximations of the velocity, of the forces, and the locations of the immersed boundary, okay? So let's do the most important and oldest application of these equations, right? This is Charles Peskin, the person that first proposed this methodology. He works at the New York University, Curran Institute of Mathematical Sciences. And I will show you some, here is an interview. I will not have time to make it completely.
Mathematical models to make new discovery.
In this video, we will discuss about.
I can certainly put available my slides, and they have the hyperlinks to all the materials that I used here. So you can calmly listen to the interview and everything, right? So instead of listening to the interview with you, I will just show you some old and some new simulations that were performed along many decades, right? These are the first simulations. Here you have a two-dimensional geometrical model of the heart. You cut it and expose the left ventricle and atrium, right? And this is a model of the mitral valve inside the inside the left hand side heart. And this is a computer simulation. This is not animation. This is animation of computer results. So you see here the some features of the flow, some vortices, how the valves behave, right? And at that time, in the 80s, he used this 2D mathematical model of the left heart, even to propose some modifications of certain artificial heart valves, including patenting of certain designs of valves. Ele patenteou alguns tipos de válvula, né? Why anyone is willing to do this? You see, this is a computer-aided design tool. You can change the shape of the valves. You can study what the fluid flow, the blood flow will do, and you can try avoid certain phenomena that is not good for the blood. For you can avoid jets, you can avoid too much vorticity, you can try to avoid certain degrees of turbulence. So this kind of modeling works pretty well for computer-aided designs of, for example, artificial heart valves. So this is a model that were developed in the 80s, 40 years ago, basically, right? We have also more recent models, three-dimensional models. These are from the 90s. It's 30 years ago already, right? So here you see just fiber structures, right? The heart is made out of, it's like a wool with elastic fibers going around a cone or something geometrical shape. So here you see the aortic and the mitral valve and other valves as well, with certain layers of muscle removed so you can see what's going on inside, right? So this is three-dimensional, and you can see the heart pumping, and it's a very old model already, and there are more new stuff they are working with, okay? So just to have a different angle. This takes many hours, many days of supercomputing, okay? This is very computational intensive, right? So here you see valves and the heart chambers and pumping, and you're ejecting the flow and everything, okay? There are other works nowadays that these simulations can be used to. For example, you can design, you can make projects for the artificial, not heart valves anymore, but left ventricles. You have some devices that replace the functionality of the left ventricle of the heart. So this is a ventricular assist device, right? And it's installed in the heart outside, right? So you have to perform simulations to understand what happens with the blood flow coming through this tube, right, to this pipe, and going back to the arteria, right? So this is an application that benefits a lot from this kind of methodology and simulation, okay? Other than that, I can mention, for example, numerical simulations of the entire network of veins and arteria, right? This is arterial pressure, and it's a mathematical and geometrical model developed here in Brazil in the Laboratório Nacional de Computação Científica, Rio de Janeiro, okay? These are some applications that this methodology are applied already or could be applied to give you information of very important aspects of the circulatory system and how flow happens inside certain engineered devices that helps the heart pumping the flow and everything, right? So just to be a little bit outside of this kind of world here of applications, here are some other applications that methodology can be used for. These are some simple things that I did with my students a while ago. This is, for example, channels with ball valves, and you have a piston over here, up and down. And at this point, we are studying the profile of the flow inside these chambers, right? This is two valves I have here, and this is a piston. Here you see, I don't remember exactly, this is probably the pressure field in this example, okay? Other example, these are pretty old already, but it's relevant for me at least. So here I have a channel and I have flexible, up here on the top, you have a flexible valve mimicking, for example, heart leaflets, which is flexible, right? So these are quasi-rigid structures immersed in fluid, cushions, and this is the flexible leaflets of the valve. The ending points are tethered to fixed locations in the domain, and these line here are just elastic connections, okay? So forces here are of different kinds. So this is to show you the flexibility of the model. For the cushions, we just have to use Hooke's law. So we have like stiff springs connected to the domain. So points here won't move or won't move much. Here I have the mathematical model that I explained earlier, based on elasticity of these leaflets. And here again, connecting the ending point to this fixed location in the domain, I have, again, Hooke's law, but with much smaller stiffness for the spring here. Okay. Here I have a different situation where I'm trying to model a rigid leaflet for some kind of valve, okay? And this is all the connections that I have to include, connecting points in the discrete model. And every blue line that you see here is like an elastic connection with a stiff spring. Okay, so this is a mathematical model of a rigid structure. What happens here is that I use very high stiffness, so the rigid structure won't change much its geometry. Okay, and here you have markers that flow with the fluid velocity, and you can observe formation of vorticities, vortices, and everything. So behind the cushions you have vortices. Here you have perhaps formation of jets. So this study is exactly for this kind of observation, and you have to change the form, you have to change the geometry of the cushions, so you will not favor formation of vortices, or you will not favor the formation of jets and things like that. Okay. Another different twist that you can give to this formulation is that the methodology is itself extremely expensive from the point of view of computational time, and you can use to it in conjunction with some local refinement. So there is much going on around the immersed structure, and you try to put a zoom, right? You have to look at this neighborhood closely. You refine your grid in space so much that you can describe better the flow in the neighborhood of the structure with a smaller cost of the computational time. Okay, so this is an approach intended to save costs and focus on the most important regions of the flow, right? This is some tool that I developed in my work through many years. So just to show you an example where we can use it, these are simulations that they have nothing to do actually with immersive boundaries, but it has to do with computational combustion. A student of mine performed a few years ago, and we have used local adaptive mesh refinement to save computer time, and we refine close to the interface of this flame. So we don't have to use a uniform fine mesh for the entire computational domain. This is three-dimensional. And just to, I don't know why it's not working.
Sorry,
it's working
Professor.
outside.
We have run out of
all the
time. I
time.
don't know.
Okay. Yes, okay.
You can make your final conclusion.
Yes, I will do.
Thank you.
So, okay, so this is just how it goes. Thank you for reminding me of my time. I just lost track of it. So I am available for questions, and you can reach me in my email if you want, and I will see with the organizers how can I share these slides and links and everything else. So thank you so much, and I will stop. I'll quit here. Okay.
Thank you very much, Professor Roma.
I don't know where are you. I cannot see. Okay.
Okay. There you are.
Okay.
Maybe we have time for just one question. If anyone has a very quick one. If not, let's take Professor Roma again.
You can call me. You can reach me at any time by using my email. I'm available.
Okay. Thank you very much.
Thank you.